In mobile health, we want to monitor and understand complex health behaviors such as smoking, drug use, stress, and heart disease. Over the last few years, there's been a lot of developments in sensor technologies, and with sensor integration on platforms like smartphones, we can now aggregate different modalities like body temperature, heartbeat, and respiration. And the problem becomes how to integrate the information from different devices. So here we consider integrating different sensor modalities into a cascade and try to come up with a framework that runs in real time, respecting constraints in terms of feature availability and computational complexity. In Cascaded Classification problem, hard decision rule is used, but previous work on learning cascade classifiers is based on soft cascade, which uses a noisy AND combination rule. The output probability is the product of the probabilities of different stages. The objective function for soft cascade doesn't know anything about the ordering of the stages, but a cascade is still operating using hard decisions, which is not a good match to the training objective. To address this problem, we propose an alternative combination rule where the output of each stage gates the computation in the subsequent stages. The gating is performed using a normalized logistic function g, which has a parameter alpha. With a sufficiently large value of alpha, it approximates the step function, which is actually used in the cascade. Hence, we call the proposed framework firm cascade. We further extend the same idea to the case of directed tree-structured cascades. The motivation for considering this extension is a setting involving multiple sensing devices, all potentially operating in parallel. The tree structure matches the applications in mobile health, where the network typically consists of a collection of wearable sensors that communicate only with a smartphone. In our experiments, we consider datasets in smoking puff detection and human activity recognition, and look at different linear or tree-structured cascade models where each stage has access to the subset of features depending on sensing modalities. We perform a stratified cross-validation to assess the performance of different models in terms of computation time and accuracy. Using a per t-test over all folds and models confirms that our approach results in models that are statistically significantly faster and more accurate than the soft cascade approach.